Hello boys and girls. So in the last video I talked about the continuum hypothesis. I wanted to talk about the power set and subsets. There I talked about in a context of infinite sets. This video will be a little bit more basic. We will just talk about finite sets. And it will be coding and a sort of continuation of a video I did a year ago. In the video how to write all the books, I coded up a stream of strings, and the strings were all the possible strings from a given alphabet. So I will call this the alphabet. This is basically just the set of characters that can be used to form the strings. I will call them codomain because they are everything that can show up in that sense, right? Just FYI, I have also like this sort of classical active power set operation on these finite objects. A video on that in various languages, and I have also this dependently typed implementation where I contrast this Idris to Haskell of the implementation of this power set operation. And this power set operation, right, and I mean in this generating finite sense, we are also going to make use of in this video. Here in the background, you see the sort of thing that we will get. This is our all these graphs from a domain of 5 elements to a codomain of 5 elements. I can zoom in, though it gets a little bit pixelated. Looks like that. And with that said, I would say let's jump into the coding. Of course, subscribe to the channel as always, and let's start here. Okay, so these are the 100 line of Python that we were going to go through. Their plotting is there. We'll talk a little bit about representations of functions, and in the end I come to what I really want to get at, the characteristic functions and this cookie cutter style of generating subsets from a set. And I do it to contrast it to what we are going to talk about in another future video, namely power set operation in set theory in a constructive context. This is basically the simple exponentiation function space version of what we're going to deal with there. Okay, so I'm plotting library, of course, because I'm going to do these plottings. I'm not a fan at all of matplotlib, by the way. If you're into Python, this is pretty disgusting API. The historical reason being that it is designed to make the use for MATLAB users easier. That was the history why it's so you can use it for years and still don't know what commands to use. Okay, but that's just an aside. Then I have some utility pretty print functions. I'm not going to go through the syntax and this Python join operation and so on, but this is just to plot nicely, as you will see in a second. And here we already have this make words function that I explain in detail in this write all the words video. So I'm not going to explain why it works. I do that in this other video, but suffice to say, what it does is you pass it this codomain, or you pass it basically a list of characters, and the list of characters is essentially the string of distinct characters, and then it gives you this make word function gives you all the combination up to a certain length or repetition, if you will. So if I run this, then from this alphabet of ABC, ABC, we get everything that you can form from it up to length 4, right? Including the empty string here at the beginning. And I could tweak the order of how things here are added up here, and then maybe it would come out in alphabetical order, but that doesn't really matter, right? We could also order it as an afterthought. These implementations, of course, they don't use this Pythonic types, and it's very brute force. So this is not optimized at all to run efficiently. It's just to get the right information out of it. Okay, and here for another example, if I make the domain smaller and the codomain bigger, right? So I say codomain only because it mirrors the language that we're going to use later, and it is a codomain in the sense that everything that can arise, everything that you can map into are these strings that are listed, right? So the strings form the output, the image of these functions, if you will, and it is a domain in the sense that this number defines how long, like how many of these outputs there are, right? Okay, so let's just run this again, and we see, of course, here all the strings of up to length 2 from these symbols codomain. And I'm going to use this now for defining other functions. So firstly, I'm going to define this list functions function. What it does is it takes a codomain, like it takes the objects where it maps into, and then it takes a length of the domain, and it produces all the lists of these codomain objects of a certain size. Basically, it's just a restriction of what we already have here, right? I produce all the words, and then I filter out everything that is not exactly of the length that I'm interested in. So this is super inefficient. I produce everything and then I throw away a bunch of things. And if you run that with X, Y, Z and 4, we get all the lists or all the strings, however you want to call it, of the size 4 with all these codomain objects like X, Y, Z in this case. So no surprise here. This is basically just a subset of above. By the way, there is this itertools implementation in Python already. This will be much more efficient if you are looking for that. Also, I talked about the itertools with some guy on Python Discord channel, and he said if I make the video, I should give him a shout out, but not even mention his name. So here I'm doing that. Okay. So, and then now for a short intermezzo, right? So I talk about functions, and I can also plot this differently. So if I remove the pretty print here, right? If I just do a print instead, then I get, of course, the same information, but it not like joined together. So I have these objects here. And of course, you can understand these as functions, right? These are functions from the domain of the index set of the list. So functions from the set 0, 1, 2, 3 to the codomain that consists of these 3 characters, right? So this is representing a function in a sense that the number 0, the index 0, right, is mapped to X. The number 1 is mapped to Z. The number 2 is mapped to Z, and number 3 is also mapped to Z, right? In this sense, this is a function. And what I'm going to do now is I make it a little bit more of a function in the sense that I will rewrite this just for the sake of it. These sort of list functions, as I call it, list funs, to not just take this range, this finite set of numbers as a domain, but any other domain, any other strings, for example, or other at least Python objects in this implementation. So as always, these implementations, of course, are in the gist below if you're into that. And here is this short section about rewriting it to a dictionary, also Python dictionary. So I have here this function, list function to dict function. I give it a list function, a list of things, right? Interpret it as a function. I give it a domain, and the domain should have the same length, of course, as this list function. Because the length of the list is the size of the domain, right? For example, in the above example, the lists of length 4 correspond to a function with domain 4 elements 0, 1, 2, 3, 4, 0, 1, 2, 3. And then I use this Python dictionary comprehension, get the index out and map the index. And instead of just using the index, I use the nth entry of the domain. And that's how it goes. That's very easy. And then given this function, I have this new function that actually takes a domain and a codomain. And now I can freely choose what I want. In this case, I use, again, these lists of characters as domains and codomains, where they are, of course, like as a function, then these characters must be distinct from each other. And I do some examples. So if we do an exit here, what does that look like? Okay, so this is how that goes then. Okay, so this is the same information, right? Except now, instead of 0, 1, 2, 3, I have a domain which is other letters, A, B, C, and D. And I print here in this representation, I use my print function defined above to actually show you which element in the domain is mapped to which element in the codomain. Okay, this is really straightforward, I suppose. And also I print out then the theorem, right? That since I produce all these functions, and I produce all these functions because that's what this list funds does. It gives me the function space. Then there's the correspondence that if I have a function space from domain to a codomain, then the number of functions in the function space is the size of the codomain to the power of the size of the domain, right? So this is just this relationship. This is the exponentiation, and I validate that, and that's why you have here the validation. This is actually true. And I can go full circle. I can now go back and instead of using some generic letter, I use actually, again, just the range, the numbers from 0 to something. Then what I will get is what essentially amounts to, again, a list of natural numbers. So this is also like this function that maps 0 to 0, 1 to 2, and 2 to 0. Okay, and so now that I have all these tools, I mean, I will not use the dictionary anymore in this video, but now I can produce all the functions. I can easily plot them, right? And by the way, like for sure on a computer you have finite computational memory anyhow. So really all the functions will be, in essence, these functions. You have, of course, abstractions where you talk about uncountable set and so on, and then you can in principle pick from an uncountable amount. But then you have like a whole hierarchy of more constructive approaches to mathematics, where you actually like take note of the fact that, to actually have an input argument, it might have been to be either describable or at least random generatable. And so without going into much philosophy or history in this video, there is of course schools of mathematics, let's say the Russian school, where the notion of function is much more restricted than in a generic classical Zimmer-Fraenkel set theoretical case, where everything, like where any two sets give you a function space, and then the amount of graphs, the amount of functions in between these domains and codomains is everything. In a more constructive setting, there might be some bounds to that, and then just to give a shout out to that, right? And you have theorems like every function is continuous, which really comes from the fact that what you consider a function is just something different than in the classical context. Okay, I hope that made sense, my short rant here. Let's go on with this Python code. So I restrict myself to just functions between these ranges now, right? These numeric list functions, let's say, that's why I call it. Which means that the codomain is also just this range. And I want that because then I can use it to plot, because Python understands if I give it 1 to 3, that these are disordered objects, and on the graph I want to have the 3 above 1. If it's just called XYZ, then this might not be as clear how to actually make a plot out of that. So here nothing happens. I just reuse this list funds and choose as codomain this range, which means this function doesn't take the codomain as input argument anymore, but the codomain size suffices. And then I also, like, this is just a wrapper. This is just the same function, but with a pretty print. I plot all these errors that you saw before, these maps to errors, and also validate the cardinality, which will be true in all of the cases in this video. Okay, so as an example here, I choose domain of size 4, codomain of size 4, and then I implement just some plotting to take all this information and put it in something which is more or less a rectangle or more or less a square. That's why I do some computation here. This is just the edge of the size of the plot. So there's really just using the plotting library that I don't even like anyhow. I generate all these numerical list functions. That's why NLFS. And then I plot them all. I plot them all the 4 to the 4 functions, and then I show it to you. Okay, so let's do that. Here I think we have to wait for a second. Okay, there it is. So here we see this is our 4 to the 4, so 8 times 8, so that should be if I'm not, no, 16 times 16. Is this 200 elements? Okay. I don't want to make a fool out of myself, so I guess it's roughly 200 if my guess is correct. Anyway, it's 4 to the 4 functions, and now I can do this for any numbers, right? So for example, here the domain is 4, so they're like, can I zoom in here? It's a little bit stuck here. Okay. Oh, I cannot zoom in because I have not saved it as an image yet. It's just this Python figure thingy. In any case, here are, like, if you look at that, if you can see my cursor here, 1, 2, 3, 4 possible domain values, and then there's also 4 codomain values. Maybe that can be seen here, right? First value is down below, then the second one is up, then the one is the second, and this is the third. So this is that. Let's do this again, but with some smaller numbers. Let's say 3 and 4. So the codomain is 4. That should be quite a bit quicker. Okay, so here maybe we can now see it clearer. Now there's just 3 values in the domain, but still 4 in the codomain, so it jumps around. And what you see in the caption of this video, and also in the plot I showed you at the beginning, I think I've closed it already, is there was it for 5, 5. And if you have enough space, you can go on with that, if you have any use of that anyhow. Okay, so that was that. Easy enough. Let me comment this out. And now finally we're going to talk about characteristic functions, right? This is the end of the code here. Even fits on one, almost on one screen. So if you took note in the video where I talked about all the axioms, right? I had this very constructive approach in the sense that I listed the constructive axioms first, and only then I introduced the law of excluded middle, right? In this, in that video, and instead I discussed this in this video. Instead of the power set axiom, there I used the exponentiation axiom, which says, like, it's a set theoretic axiom. It's not as easy to formulate as the power set axiom, but still easy enough. And it says that for all sets, the sets of functions, where functions is defined in this graph sense, like, a set of pairs that is functional, and the pairs correspond to the key value pairs from the domain to the codomain. And the axiom was there, all these these sets of pairs, these function spaces exist. And this is something this I want to emphasize this here. This is something very different than saying that for any set all the subsets exist, because if you say all the subsets exist, then you range over the domain of this course, in this case sets, over all sets, and take all the sets that are subsets of it. This is this very impredicative notion, and I made an hour-long video on impredicativity a month ago as well. So this is the one notion of subset, and this is a priori, if you don't have excluded middle, for example, not to be confused with the notion of subsets that we are going to discuss here in this last screen. Namely, that you have some given set, and then you generate, if you want, all subsets by cutting out from this subset, right? When you have a finite number of symbols of finite codomain, and you want to generate subsets of it, then you can also use this make words function that I have used at the beginning of this video, right? Then you start from the bottom and generate everything. This is the up way. What we do here now, what we are going to implement is this sort of down way. You start with the given set, and then you say what do you want to cut out. You use function like a predicate, or to implement a predicate to say which do you want to keep and which do you not want to keep. And there you see that this binary notion comes in. There's there must be this sort of decidable notion of yes, I want to keep it, and or otherwise, if the predicate that makes the decision is computed to not be positive, i.e. it's negative, then you still have this decidable choice made, and then you reject the element. Okay, so I emphasize this again just because it will look a little bit different once we take decidability seriously in the next video. So what do we have here? Again, I'm going to use the implementation that we already have, this numerical lists of as representations of functions, right? And we are going to model the Boolean type as this list containing either two elements, 0 and 1. And so we set up true and false according to this model, right? In particular, for our accept implementation, like keep, for making use of characteristic functions, xi, key, we need the positive value to be this one. If we set up the bool using these values anyhow. Okay, so yeah, you can see here, given a characteristic function, which is just another name for a function, then maps into this 2-element set, and some value that has to be in the domain of the function. I could make an assert here that this x, in our case it's just a number, must not be bigger than the length of the list. Bigger equals, and we say we accept the element, of course, if the return value of the function, of the characteristic function, is the true value, right? If it's 1. And then again, I take some domain. This is just some random string. I can use here anything, like I can say hello, let's say. First word that came to my mind. I mean, the first word was hello, but I don't want to have 2 L, so that's why. The bool I define it in the natural way. Like I define it here as a tuple, but I can also, like in Python, that for what we do, there's no difference to defining it as a list. Probably also a set would work. Yeah, actually I could probably wrap this into a set like so. But this is just FYI. Don't need this here. That doesn't matter. And then given that fixed domain, right? Everything I do in the rest of the video has access to this global values DOM and bool. Then a subset being cut out from the domain via a characteristic function. Just functions like that for every character in the domain, right? For every element of the full set from which we want to cut out, we add this character, this value, to the return value set, or in this case, again, this is just Python. I coded this up as an iterator, not as a set. So you can also turn this into harder brackets, but okay, let's leave it for the moment. Doesn't matter for this at all. It's just an iterator. It's effectively the same as a list here. So keep it if it is accepted. I mean, okay, I'm talking long here, but it's pretty clear anyhow, I suppose. And then finally, what we do is we generate all the we generate all these for what do we do here? Yeah. Okay, we generate all the characteristic functions. I was a little bit confused because I thought we're going to pass this bool directly, but instead, what I do is I just pass the number here because that's the way our numerical list function was set up, right? I don't even pass the codomain, I just pass the length. And I was a little bit confused about that for a second. But so this end up being the characteristic function because they all map into this codomain, which just has 2 elements. And then I compute all the cutouts. These are all the cutouts from DOM because DOM is hard-coded here of this domain, like this 4-letter word. I compute all the cutouts by cutting out via the characteristic function, and then I plot it. So let's do this final run. Right. So the printing function from this numerical list also plots us, gives us this characteristic function. So here we see all the combinations of 0, 1, 2, 3, like 4 elements, which is the length of the word hello, being mapped to either 0 and 1. Not surprisingly, this is 4 to the power of 2, so this is 16 characteristic functions, and corresponding we have the 16 subsets of hello, right? And that's that. We already had seen this like the set of subsets as a subset of this make words function, but the make word of course has also repetitions, whereas the power set, because we're dealing with sets, ought to not have repetitions. Let's do a longer word again. Powers are okay. Some word, I don't want to repeat the characters, but just to get some little bit more interesting as a result here. Yeah, so here this has like 8 to the power of 2 return values. These are all these subsets. And again, I represent everything with lists, even the functions and the sets, but I hope the translation is clear when I consider them as functions with the indices at their positions, or when I consider them like here just as the sets where the ordering doesn't actually matter. Okay, so that's that for this video. It was a little bit more pedestrian, but I now don't have to refer back to the characteristic like functions. I don't have to code them up again in the next video, which will be about the power set in a constructive setting. Take care.